So this is this is the final examination of Kaiyu Zheng for the degree of Doctor of Philosophy in Computer Science. Computer Science is bolder. The candidate has satisfied the course requirements for the degree of Doctor of Philosophy in Computer Science. The candidate now appears for the final examination on the thesis entitled Generalized Object Search. So the defense has now been discussed. All right, so I'll just introduce Kaiyu. So I'm Stephanie, I'm his advisor, obviously. And Kaiyu has really been a joy to have in the lab. When we started out, he had really giant ideas for how he wanted to transform robotics and make a robot that could act autonomously. And George and I were trying to rein him in and help him scope the problem. But he actually went off and did a really big thing that makes robots act autonomously and applied it in a lot of different settings. And he's one of those students that just goes down the lab and makes the robot work, which I think we all find very exciting. And I feel like you're a machine, making software packages that have been released on GitHub. And you look at the webpage and it's just so professional and documented and everything. A lot of the lab has been using the POMDP package that you wrote and the Spot infrastructure software that you wrote. He's done a lot of things with collaborating with some of our funders like ARL and DM and flying in, making something happen with them and without letting up on his own work. I think his work is really transformative in the field of robotics because I think this problem of object search is sort of fundamental to making the robot do anything. You got to find the thing first before you can pick it up or open it or operate or do anything else on it. So he's done a lot of foundational work thinking about the models for that, and then very practical work making it happen on a variety of real robot platforms. So I am very happy and honored to have you as a student. It's really been a pleasure and a joy to have you in the lab. And we're looking forward to your defense. So thanks, guys.
Thanks, Stephanie, for that introduction. I hope everyone is doing well, and thanks for coming. And thanks for people on the Zoom. Thanks, Leslie, for taking the trip. And also Michael. So yeah, so before I start, I just want to also just acknowledge all my collaborators. And without them, the work wouldn't be possible. So, okay, let's get started. So the kind of work during my PhD has been about this kind of setting in this picture here. So you see Spot in the kitchen area. That's the kitchen in our lab. And basically, you see objects all over the place. Could be on the shelf under the couch or on the counter in the sink. So the Spot here, it has a gripper that has a color camera, and that's the only color camera on this robot. So basically, if we want the robot to search for something in this room, what the robot would have to do is basically figure out how it's gonna move its camera on the gripper to around the space to find the target objects, and that's naturally essentially you're gonna figure out a sequence of viewpoints to look at, and that's a sequential decision-making problem. So why do we care about this problem? So for robots being able to search for objects, that's a valuable skill both by itself. So for search and rescue applications or for elderly care, if the robot can help an elderly find their missing pair of glasses. And also, the ability to search for objects is actually a prerequisite for many downstream tasks. So, if eventually the robot would cook, you'd expect it to be able to find ingredients in the pan before it cooks anything. So, speaking of object search being a prerequisite, here's a slide from Jacob and Andrea's talk at RLDM this year. It shows the output of a large language model that takes in a high-level language command like pick two apples, then heat them, and output a sequence of lower-level commands like find the apple, pick up the apple and on the table, and so forth. So what you notice is that for all of these examples, they begin with find something. So literally, finding an object is a prerequisite. for whatever downstream task you're doing. And you may wonder, yes, this could be an important problem, but is it actually difficult if it's treated as a single step in this lower level sequence of actions? I'd argue that it is challenging, and you could see that from like a scenario like this. So this is again in our lab, a different room, and we have Spot on at the back, and we wanted to search for a book that is on the table in front of the monitor. So what are the challenges in this setting? So first of all, the robot only receives observations through its gripper camera, which is has limited field of view, and that's partial observability. And when we use like object detectors or segmentation, those are noisy and make mistakes. So that's perceptual uncertainty. The environment doesn't just contain the robot and the object; it also contains many other objects, and it's not built for the robot. So it is a complex and unstructured environment. And because we want the robot to search in a human environment, it would be great if the robot can take in human input like language hints. Like, for example, the book is in front of the monitor, and be able to like use that to search more efficiently. And last but not least, we don't just want the ability to search to work for this robot in this room for this book. We want this ability to generalize across different environments and across different robots. So the goal is really to make the ability to search be like an off-the-shelf thing that the robot can just have. So how do you really go about solving this problem? Well, if you can break down, when you're searching for an object, you can break this question down to two sub-problems. First is which region should you search in, and second is how do you search in a region? For the first question, there has been a lot of work dating back into the 90s, and the focus has been on scalability. So can you sort of like figure out which region to search for over like an entire room or entire building, and then also leverage like common sense. So basically relations between like the category of the room and what you're searching for to reduce initial uncertainty. And then in the very early on in the 90s, this was one of the pioneer works. Sorry, so basically, in that paper, he says, once such a subregion has been selected, however, a harder problem arises, namely the problem of how to select views that search the subregion. This problem is not really addressed here. So indeed, the question of how to search within a subregion is a harder problem, and it's proved to be empty complete also in the 90s. And as a result, people have pursued like greedy algorithms, basically selecting the next best view instead of treating this as a spatial decision-making problem, or make simplifications that are less realistic. So simplifying the 3D to 2D, or basically limiting the set of viewpoints that the robot can perceive from. So other efforts focus on, for example, on the left, here's a human robot that's able to like both plan how to move its feet and also how to like move around to detect the object, find the object behind the board. And this is an impressive system, but it is built specifically for that humanoid robot. On the right, there's, recently there's a lot of effort in like this kind of data-driven approaches where the agent takes in a raw image and directly outputs the action. And so it has received a lot of attention, but so far this approach has mostly been evaluated in simulation, and it's yet to show whether it generalizes across real environments and across real robots. So the main thesis of my research is that by modeling the object search problem as a POMDP while exploiting structures in the human environment and human-robot interaction, we can achieve an effective and practical system for generalized object search that addresses all of these challenges. And so here's an overview of the projects I've done. I arranged them on this axis from robot acting in the human world to interacting with humans, and on the side of acting. So the first part is like 3D. So basically, searching for an object in a 3D environment, multiple objects in 3D environments, in a 3D environment that exploits the structure of octrees. and then correlational object search, where if you're like searching for a small object like the pepper shaker, your detector may make mistakes like false positives or negatives, and then but it may work better for other classes. And how do you like leverage the correlation between those to find how to detect objects faster? And moving towards interaction, I consider a problem where a person gives a spatial language like the car is behind Chase Bank, and can the robot make use of that and search more efficiently? And lastly, on the side of interact, I sort of started this project and did like a pilot data collection for this problem called dialogue object search. It's about a robot when it is searching for something, enable it to have a dialogue with a person that can give additional information. So that's a hard problem that will probably continue after my PhD. But the way I wrapped up is I sort of like went back to the 3D object search and made it a system and package that actually hopefully will make this more available. And that's called generalized 3D multi-object search. So in this talk, I will go through all these projects, and so I'll focus more on the impact and basically the problems. And if I'm missing any details and if you have any questions, feel free to ask. So before I dive into any of them, I'd like to just review POMDP and why we use it for object search. So POMDP it stands for partially observable Markov decision process. It's defined as this tuple, and it models a very natural model for a sort of like from an egocentric perspective how a robot interacts with an environment. So you have a robot that's placed in an environment, and the environment has some state that is not unknown to the robot, just like you're finding an object and you don't know where it is. So because the robot doesn't know what the state is, it basically maintains a distribution over the possible states, and that's called a belief state. And the robot, it can like take an action, and that may impact the environment to change its state according to some transition function. And then the robot receives observation through its sensors and according to some observation model. And then basically after receiving the new observation, the robot can update its belief. So basically like reflect what it is currently observing. So the objective of basically solving POMDP is to find a policy that, given the current belief state, find a policy that maximizes this discounted cumulative return. So it is well known that it is intractable to solve most practical large POMDPs. And what people do often in practice is do online POMDP planning, and the idea is really simple. So you can just think of planning as a search problem, and you start with like your current belief state, and you branch on your actions, and the entire search tree is enormous, and you wouldn't be able to like have it all to compute your value at your current state. So the idea of like this Monte Carlo tree search based algorithm is to approximate this full tree by a subtree, so that you can like have some estimation of your the value at each belief state. And hopefully, as if you have run more simulations, then you have a more accurate estimation. But also you can see that if your tree is deep or your branch is wide, it's like kind of like less accurate approximation. So in our research, we use a lot of these basically Monte Carlo tree search based algorithms for POMDP planning, and specifically POECC that was proposed by David Silver a while ago. So let me dive into the actual projects. This first one is 3D multi-object search. The scenario is like you have a robot. In this case, this is a MOVO that has a movable base, and also a torso that can go up and down. And then there are multiple objects the robot needs to search for. They could be on the floor, on the shelf, on the table. And the hope is that if we have this ability to search within a region, we can deploy it in different regions to like basically search in a bigger space. So the way that we model this as a POMDP is shown on the left. So basically, the state is factored into the robot state, that is the position orientation of the robot camera and a set of found objects, and also the location, 3D location of the objects that the robot is searching for. And the actions are moving, looking in direction, and declaring an object to be found, declaring an object to be found in the location. And so a highlight of this model is we consider a realistic observation space. That is, each observation is a set of voxels in this viewing frustum, and a voxel could be labeled as the object, or it could be occluded as unknown, or it could be free. That indicates like free space or some object that doesn't matter for the robot. And basically this is a large observation space, and one idea that that's like sort of important for this work is we make the assumption that an object is contained within a single voxel during planning, so that we can limit this set of voxels to just one single, basically the label at a single voxel. So that drastically reduces the size of observation during planning. And the reward function is sparse. So basically, if the robot takes a find action and then the object is within the field of view, then it receives a high reward, like plus 1,000. And if it is incorrect, then it's minus 1,000. And if it takes any other action, then it is a step cost based on the distance traveled. So one basic question is, if you want to basically approach this kind of planning under uncertainty, like search for an object, you care about like what's your representation of your probability distribution. And you may use think of particles or histogram, but particles is subject to deprivation if your observation space is large. And the histogram is inefficient if you want if your search space is dense and you need to store the probability at every location, and you need to update it using the Bayesian filter. So one key idea of this work is we propose this representation called octree belief that represents this basically distribution over where the object is in the structure of an octree. And here on the left, you can see each node stores a value that represents the unnormalized belief that the object is in there. And the value of the parent is the sum of children. And we maintain a normalizer separately so that you can basically have actual normalized probabilities. And the key benefits of this representation, there are three key benefits. First is it can be constructed incrementally as observations are received. And also it simultaneously tracks object belief at multiple resolutions. So basically, without the tree being completely built, you can query the probability at any node just by, the way to do that is by sort of assuming a default value as some node that you haven't seen before and divide that by the normalizer. And thirdly, can support efficient and exact belief update and sampling, which makes it possible to do online POMDP planning. So just want to, and then in this original paper, the way we approach planning is because we have this representation over multiple resolutions of how the belief stays. So we instantiated the 3D object search model at different resolutions. And because we don't know what is the right resolution level to use, we sort of extension several of them and this parallel planning and select the one with the highest value. And here's how it works on a real robot. So this is sort of like a proof of concept system. And you see the MOVO sort of plans to look up and down, and then in this case finds the book on the table. And you can see a visualization of the octree belief there. So is there any questions so far? Amy?
So is this octree belief idea specific for three-dimensional
modeling? I mean, yes, octrees is a specific idea for three-dimensional space, but the idea of modeling like a belief in a hierarchical manner, sort of having like your the belief as a parent is the sum of the children, that could be extended to other kind of, yeah. Any other question? Okay, so
Kaiyu, can I ask from outer space? This is Iris.
Yeah, of course. Iris, yeah, nice to hear from you.
I have a question on how you're dividing up the space. So you talked about having this, you're assuming that a single object fits within a single voxel, if I got it correct. How do you know that ahead of time? And in practice, how many regions do you have?
Yeah, so the first question is, how do you know, like, if an object can be contained within a single voxel? For that, basically, like any object, so the way that we think about object location in this work is we just care about its center of mass, so it's like a point. So any object you can think of like it being somewhere in the space. But basically, so that's really like helpful for planning. But when you actually have the system and you receive observations from the real world, it could be that you have multiple voxels labeled by this object. The second question is, how many like regions do you have? Is that the question?
Yes, that's right. And in practice, how many do you have? And I guess, how do you decide that?
Yeah, so this algorithm is really like focused on searching within a single region. So it basically it doesn't reason about like whether an object is outside of the region or not. You can add that additional thing, but so basically we have one single region, and in this evaluation we did, there were two regions, and you could have an additional layer in your system that decides whether you should leave this region and search in a different region. So, okay, I'm gonna move on.
All right, thanks.
Yeah. So now we have seen this like basically proof of concept system. A question that matters more to roboticists is that how do you make this more generalizable? So when we think about like what's really generalizable, I think of them as like the things that you can actually pull off the shelf. So for example, so you think of like the spot here, off the shelf, it can do some perception, like build a map and do navigation. And it has some built-in manipulation abilities, like opening the door or picking up objects. But, and also like for these perception and manipulation, you can find like packages, for example, like YOLO or like for manipulation, there's at least like motion planning or move it that you can use. But for object search, when we want the robot to open the door, we have to like manually drive it in front of the door. It doesn't, you can't just tell it to open the door and it will find it. So this is not existent yet. So basically the focus of this project is to try to come up with a system that that can be deployed on different robots and sort of like bridges this gap. So the contribution of this work is a system called Gemos, which is a robot-independent environment-agnostic system and package for object search in 3D regions. And it takes as input some sort of generic kinds of data that you'd expect most robots to have, like point cloud, 3D object detection, bounding boxes, localization, and some configuration, and outputs viewpoint pose in 6D. And I will have like a video sort of that animates all of these, but the thing I want to point out is how we handle point cloud in this system. So here's a point cloud of of our lab, and the colored area is like the search region, and then the system sort of takes in this point cloud of the region and use it for three different purposes. First one is occupancy. So you can imagine that if I have point clouds, I can convert it into an octree. And that's like a volumetric representation of the space, and that's, you can use it to simulate occupancy. And also we use the point cloud to initialize the octree belief. So we don't want to believe like the object is in the midair, but we want to like believe the object could be around the table, which are contained in the point cloud. And also we use this sort of points as obstacles when we sample the viewpoint graph to avoid collision. And here's a demo of that, of spots to search for a cat underneath the couch. And on the bottom right, it is the view from the camera gripper camera and as a object detection results. And the thing about this is it was a surprise that I could do this like only in just 3 steps. I anticipated I could look underneath the couch because I have run this system a few times and I saw that I did that. But in this particular demo, it was actually like, it was real after I realized that the robot would sometimes look underneath the couch. I basically placed the toy cat underneath the couch, but I didn't know that you could find it in just 3 steps in this case. So it was kind of lucky. Okay, so here's how the system works. It takes in point cloud from the local region, 3D object detection bounding boxes, and the localization of the robot camera pose, and outputs a viewpoint in 60 to move the camera to, and the system underneath the hood is a gRPC based. So the clients interact with the robot, and basically the server that handles the planning. And we implement this sort of octree based occlusion. And when I place the board, like the field of view gets sort of occluded dynamically. And here's what's going on internally for that search for a cat example. The red cubes are a visualization for the octree belief. And the robot sort of like plans over this viewpoint graph, and the viewpoint graph is sampled based on the belief as it's updated. And this is an example of searching for a cat in our lab. So we made a space so that it's segmented by the board and the table. So this could be occlusion, and it finds the cat, and it looks from a different angle before it decides to the cat is found. So, and here's searching for multiple objects simultaneously. The object could be under the table, on the table, or and also the cat. And it just shows you sort of like what happens if you keep running the system. What you see is like the robot sort of tries to look at places that it has a higher belief in, and yeah. And here's the system in the kitchen area is searching for on the counter. In this case, it is fine. So basically, this here is searching for the cat in the sink, and it does make a view, but the object detector didn't work. And here we integrated this local search, 3D local search with a 2D global search, so hierarchical algorithm, and basically finding this cat on this chair there. And the same system is deployed on a different robot in a different room, and like sort of plans to look up and down, and still searching for the cat. And this is a successful case of finding the cat. Previously, it was it looked at the cat, but the detector didn't work. So okay, and just to illustrate the difference, like even though these robots look like they're similar, but they're very different when you work with them. And to illustrate the difference, here is like a blooper when you work with MOVO, and you just wanted to like do object collision avoidance, but it runs into the, I wanted to make this more challenging to like have the cat in front of the door, but the robot isn't able to handle the collision avoidance. And this is never an issue for Spot. So, and this is an ongoing effort that sort of at VM is a company that is trying to make a replacement of ROS2. And I went to their company and tried to like deploy this system on their UR5 robot arm. I will go there again in a few days to just make sure that it works. So, okay, so any questions about this so far? Team.
So I thought it was really cool that it like went to confirm, like when it saw the cat, that it wasn't like 100%. So what made it like not look randomly all over the place, but know to take another action where it could sort of confirm its belief.
Yeah, so I think what happens is when the robot first sees the cat from this angle, it does have a positive object detection. So the belief is updated to be around there, but it is not strong enough because you have a huge penalty if you like have a wrong declaration. So the robot sort of I know it is there, so I'm just like, I didn't know that it's gonna go from this perspective. It could be that it stays in place, but it was like sort of like a particular example in that case that it goes to a different angle to look at down. And it's also possible, it could now work out if like the detector wasn't trained for the cat from a different angle. So like if you go look from a different angle, like detector doesn't work. So even if like your search system has the right belief, it may still fail in practice. So any other question? Okay. So now, so in the previous two works, basically, I just care about like the object that you're searching for. But here in a more realistic setting, the robot, like it's more likely that you lost your glasses or your keys or your credit card that you want your robot to search for you. And it's also very likely that your detector for these small objects don't work very well. But at the same time, because these objects are in a human environment, they are sort of spatially correlated with many other objects. And for example, like when you're searching for like the pepper shaker, it could be near the kitchen sink or your stove, and your detector may work better for them. So the question of this project is, how do you leverage the spatial correlation between easier to detect objects and hard to detect objects to find how to detect objects faster? And we still model this as a POMDP, and then we sort of consider the correlation as between spatial correlation between two objects as a probability distribution. Given the location of the target, what's the distribution over the other object, and that's part of the observation model. I'm gonna skip the details of this model if you feel free to ask if you're interested, but I'm just gonna dive into the results because that's what matters for this project. So here, you may not see it so clearly, but this is a table, and on the left, it's so like the evaluation is done in a simulator called Air2Thor, and it's a simulator for household environments, and it has a few different room types: bathroom, bedroom, kitchen, and living room. And for each room type, we consider like 3 objects to search for, like faucet or candle and so forth. And we compare our method, which is on the far right, to two baselines. So one baseline is a POMDP, still POMDP based object search system that doesn't consider correlation, and also a greedy next best view approach that was based on recent work that uses particles to represent the belief. The key takeaway is that for objects that are hard to detect, so for example, like the candle here, the true positive detection rate is below 30%. And for these objects that are hard to detect, like below 40% true positive rate, our approach outperforms the baselines with statistical significance in terms of the SPL baseline, which is a metric, which is a measure that's widely used in this environment that considers both efficiency and success of the search path. Okay, and I'm just gonna show you some demos. So this is searching for a scrub brush in this environment, and the environment is still 3D, so the robot plans to look up and down, and it detects like mirrors and the toilet, and basically we are sort of telling. So in this evaluation, what happens is like we imagine like a person comes along and tell the robot like the scrub brush is behind, is like around the toilet. So it uses that kind of like correlation that is sort of accurate in this particular environment, but not exact. Okay, so and then here's a different demo of searching for a credit card in a living room environment, and the detector for the credit card didn't work at all, but the detector for like laptops or payload did work. And based on like the correlation between those objects, like the belief was updated enough to be strong enough to be there. And in the middle, that's the baseline where you don't consider correlation. And what happens is that the agent sort of relies on just luck to detect the credit card, and it actually did so eventually. So is there any questions about this, Ellie?
Yeah, where do you get the correlations from? Are these like a prior that you guessed, or is it learned?
So okay, so in AR2Thor, so when we deploy the system in AR2Thor, you do know like the location of the objects. So for the environment that you deploy in, we sort of like have you know, whether the distance between the two objects is far or close. So that's like a binary kind of function for correlation. We did have a baseline that tried to estimate the correlation from the training. So we did train object detectors. So we had some training environments, and we sort of have correlation that's estimated by the statistics of like how often do these two classes appear together, and that's like the that's a different baseline. But we don't focus. We sort of focus on the planning side instead of like what's the best way to represent the correlation. And the thing to know is that the correlation model is just a generic probability, conditional probability. So if you have a like conditional probability condition on the location of the target and what's the probability over the object that's correlated with, and if you have like a graphical model or some other way that's trained on a bigger data set, you can like integrate that into this observation model. Does that make?
Maybe I'm still confused, but I can ask more later.
Yeah.
Like so there are kind of two alternatives. You said there's one that's kind of in general, credit cards tend to occur close to laptops or tend to be near laptops. Versus like in this scene, we know like go find a credit card, it's by my laptop.
Yes, exactly. So it is the second scenario that you're saying. Basically, the question is whether in this evaluation, like the correlation is like based on some prior data set, or it is specific to this environment. It is specific to that environment, but it is not exact. Like it's not like I see the laptop and then that exactly informs me the location of the credit card. It is like I see the laptop and then I update my belief so that like around this radius it could be, but the radius is sort of based on the distance between the two objects.
So it's much like correlational is maybe an odd term because it's more some exact information the robot's been given, like you say, the toilet brush is behind the toilet, not like. Right.
So so I'd say that the correlation is really it describes the probability model. Like this is in this evaluation, it is true that we sort of use this environment specific, but it is still sort of spatial correlation between the two object locations. So
it's a correlation based heuristic.
Yeah, you could.
But you had the baseline that was like true.
Yeah.
A priori correlation.
Right. I did have a baseline that.
It doesn't matter where the model comes from.
Yeah, I mean, they seem like they're addressing two very different problems, right? This kind of general correlation is something like, hey, go find the pepper shaker. And I'm like, okay, well, I'm going to start by searching places where I think it's plausible that the pepper shaker would be based on what it tends to occur around. But you would probably need like an out for that system, because if it's not in any of those places, you get caught in this loop where you just keep looking at things that it tends to be around. But if you've truly lost the pepper shaker and it's nowhere near the salt shaker or even in the kitchen, right, your model's gonna be confused. That's like a different kind of use case where you're like using some prior touch search than the prior where I know I'm telling you where the pepper shaker is roughly. I'm like, hey, it's by the fridge, and there's still a search problem that has to happen, right? Yes. But they seem like two very different kind of worlds that the robot could be in.
So basically you're asking, like the two scenarios is like, one is like the object you're searching for may not be there.
Right, like there's one where you're kind of exploiting priors, but there's more uncertainty. And so you're like going by heuristics or something that might actually be false, versus one where you've been given actual information that is presumably not wrong.
Right, so I think the question is like, can this system handle if the case when the object is not in the scene? So
I don't even know if I was just trying to understand, or first I was trying to understand which of those worlds we're in, and now I'm just trying to understand if you agree whether those are two different worlds or if I'm missing something. Those are
math
actually
is the same.
right, I don't think those are different.
Yeah,
they sound the same to you.
the underlying math is the same.
It's unless you take advantage of the fact, like this is known, it's probability one.
Right, but
then
that's
you
what
can
I
do
feel like
special case stuff.
Right, they shouldn't be treated as the same, right? Those are very different things. Like me looking through a house where I have no idea where something is, and so I'm trying to use some kind of common sense background knowledge, but that could be completely wrong. Like
So-
these would be like weirdly in my cat's litter box.
Because they're different because in the first case, the probability is peak error.
Yeah, it could just be given as a probability is.
I think
So,
they're
I'd say, okay.
to me,
so-
they're different because one is like an assumption, which very much just could be straight up wrong, versus like, so I view the case that we're in where you say like, hey, it's by the salt shaker, as similar to the spatial language thing. It's like you've been given this information that is actually fact. So you should
Right.
keep searching around that area until you find it. Right? 'Cause that's
They could have
knowing
lied.
that it's there.
Yeah, it's possible that the information is not accurate and the system wouldn't need to change. Like basically, if I'm searching for this credit card and it's not actually there, but the correlation information is wrong. What happens is like the robot may not see the credit card in this location, but then everywhere else becomes more likely, and it will basically try to like search elsewhere. So yeah, I think I think you're talking about, it is true that you're talking about two questions. So the first question is more like about like the prior that you begin with when you search for something. So if the question is like when you search for a pepper shaker, your prior knowledge sort of helps you reduce the initial uncertainty. And it is possible that this prior knowledge is wrong, but then the second question is like how to do the search. And that system can still apply if your initial uncertainty is inaccurate. Okay.
Yeah, no, I agree that the math in the algorithm is the same, but they feel semantically different. Like you would want the robot to treat these worlds differently or these sources of information differently. But we can talk about it.
Yeah. I think in practice you do have maybe like a separate system component that handles the prior, and that would be a pretty different world. That is true. Okay, so I can move on. Okay, so so the next project is moving closer to interaction, where we still want the robot to search for an object like ice cream truck. And in this case, we assume like a person comes along and tells the robot the ice cream truck is behind the ticket booth, and it contains like special prepositions like behind it's possibly ambiguous to the robot and subjective to the human. So the problem is how do you sort of take this spatial language and interpret it to update your belief and then search for the object more efficiently. So the approach that we propose is called spatial language object-oriented POMDP, and the key idea is we treat spatial language as a form of observation that's stochastic, and we propose a observation model for spatial language. Essentially, when you're given a unstructured spatial language, we first parse it into tuples of. So in this case, the tuple could be ice cream truck, comma behind, comma ticket booth. So that's basically like the object, the preposition, and the landmark. And so that's like the structure behind the language. And so there's a part where in order to understand like behind, we propose, we sort of come up with a model that can predict the frame of reference for behind that takes in a top-down view of the environment. So just to basically to make it make it more concrete, and also like another key aspect of this project is data collection. So because we don't want spatial language understanding to just work in a particular environment, we want to work on different environments. And also the frame of reference prediction model, we hope that it can generalize between different city maps. So we collected a data set of city, sort of like from OpenStreetMap, like top-down views of city maps. And we also used, so this is all credit to Dennis and Becky. So on the bottom left, it's data set collected from Amazon Mechanical Turk. We showed Turker a scene of like, with a red car and a bike, and then we asked it to describe us, actually. Okay, we asked the Turker to give us some spatial language, and what you see is that for the same scene, different people say many different, very different language, and so in this case, in this project, we don't sort of assume what kind of granularity of information you're giving me, as long as you give me a spatial language that involves, spatial preposition and describes the location of an object. Then we can take in, the hope is that our system can take in this like natural language directly and then interpret it to perform object search more efficient. On the bottom right, it shows like distribution of the prepositions. And I just want to dive into the demo. So here's the demo in AirSim, and the language is the red cars behind Jeffrey's house around Renee's house. And on the left, you see basically that's the initial probability distribution, like the initial belief after interpreting this language. And it shows like a heat map, a red area around like the bottom there. So this is AirSim is like a simulator for drones. And we sort of tried this neighborhood environment, even though we didn't train the object, like the frame of reference model for this particular environment, because it sort of like uses a synthetic representation, it could generalize to this like simulated environment as well. So here, the drone is sort of like flying in the middle of the road. That's kind of unrealistic, but that's a result of like sort of having the houses as obstacles, and you have a huge penalty if you bump into the houses. So this searching, the robot sort of didn't see the car on the first try, like in that area, that's most likely. But the point of a POMDP based planner is like it can sort of be robust and go back to look at other places based on your current belief and eventually find the cat, or find the car. Too much cat. Yeah. Okay. Is there any question about this? Okay.
Right, so the actions are abstract for this, right?
The actions are abstract. What do you mean?
Like I'm just wondering, you're not like executing motor.
Oh yes, that's right. So the question is like whether I'm executing like motor control or directly like navigation goes. Is navigation goes. So okay. So here's the quantitative result. On the x-axis is the maximum search steps, and on the y-axis is the amount of successful searches. So the gray curve shows like the uniform case where there's no prior information. And what you see is essentially like within 100 steps, about 76 search trials completed successfully for the uniform baseline. And the blue one is the informed, which is like the upper bound, where like the robot begins with a small Gaussian noise around where the object truly is. And what you see is like if you just understand the landmark, where Jeffrey's house is, like, and then impose a probability around it, then it already improves over the uniform a lot. But by understanding spatial language using our approach, it improves the search performance even more. And we tried both the case of like using our parsing system pipeline, or using sort of like assuming the parsing is perfect, that's the dotted line, and that could improve the, if you have no errors in your parsing, then you could improve the performance even more. So, okay.
Is the number of search steps customizable, or is it just a fact of like some searches take longer than others?
The maximum number of search steps is customizable, is 200, and the amount of actual search steps is dependent on your case.
How should I read this curve? Is that
so the slope? Basically, the slope indicates like the efficiency. So basically, like you can see 50 there. The gray curve is only like about 30 objects. Yeah,
like a point on this blue curve, like at the knee point of the curve? Like, does that mean that only 25 search steps were allotted,
not allowed, but basically, so
I think he's reacting to the word maximum in the, like, why does it say maximum search steps
Oh.
as opposed to just search steps?
right, okay, so the reason, so basically we collected a bunch of trials and different trials completed with different steps, and for number like 25 here, it's basically the trials that completed within 25 steps.
Okay,
But they all had
They all have
to do up to
up to
200
200,
steps.
exactly.
got it, okay,
But some of them finished, but
Yes,
okay, thanks.
okay. Anyhow,
Yeah, so you mentioned you had 3 different cities or 4 different cities. So did the model perform differently on different cities, or was it the same? Like, is it easy to adapt to like a new city?
I mean, the framework reference prediction model definitely performed differently across among different cities. And here it is sort of like the average over all of the cities. I don't remember exactly like which one is better, but
we should probably finish up.
yeah, okay. Cool. So I just want to show you actually, so this is a system like prior to the 3D object search, I tried to implement the spatial language on spot. And on the left is like, with the language, and on the right is without. And I actually included the typing time, like time that I'm typing the language. So what you see is like with language, it sort of, so the language is like the book is in front of the monitor. And the monitor is like a landmark in this case. And basically, what you see is like the one on the left is like quickly reduces to that region. But if you have no information, then the robot just like searches all over the place. And in this case, like the detector wasn't so reliable. It was like prior to it was mass scarcity, and we used like YOLO for the 3D object search, but like the robots will struggle a little bit in that area, but eventually it finds the object. Okay, so I just want to, okay. So just want to quickly go over dialog object search, which is mostly like a pilot data collection. So the idea of this problem, I like to argue that this is a very important problem. So imagine like you're at your home and you're searching for a file and you don't know where it is. And somebody else in your family, like you can like, may have a better idea. And as a person, what you could do is like call them and have a dialogue with them while you're performing the search. So you're deciding what to say on the phone while deciding how to perform the search task. And those seem to be two very distinct kind of problems to plan over, but you are able to do it simultaneously. How can you make a robot do that? That's the question, and we don't know. So we did a pilot study to see how people do it. We built a data collection system that's for the pandemic, so everything runs in the browser. There's a controller who controls like the agent in AirSim that acts as a robot, and a assistant that has a scatter plot of some of the object, but may not contain the target object. And things that run on like AWS, and we make like the participants be able to have a Zoom call, and we record the Zoom call. And here's an example done by Monica and Jason, one of my collaborators. And here is sort of showing, I don't know if you can hear anything. Sorry, but basically Monica is interacting with this interface and speaking, and sort of like they're having a dialogue. I'm not gonna play the whole video, but basically the fridge can be opened actually. So here is like the one example trial that we collected. So on this axis is like the timestamp, and we sort of overlay the dialogue on the timestamp and some snapshots. So basically the takeaway of this is even though the language is very unstructured, for this task of object search, we can identify just a few intents that's necessary. In particular, the interesting ones are behavior description, environment description, and belief description. So for behavior description, for example, let me check the fridge. So it's like, what am I gonna do? The robot is trying to say what I'm gonna do. And environment description is like I don't see the apple, or I see an egg. So it's trying to describe what the robot believes is true about the environment that's based on its observation. And belief description is like, I don't think there's anything down there. So it's like basically describing their belief of the apple that's not in there, but that's like not based on the observation. So the thing is that even though it's a very unstructured, if you come up with a system that can output this kind of intent and translate that into language, maybe you can have a system that can do this. And then there's artwork that, recently that have tried system like this using large language models, and I'm happy to discuss if you have questions. So just as an overview, this is like the projects I did, and I just want to like end with a quick summary of future work. So still thinking about this axis of robot acting in the human world and interacting with humans. And let's say your ultimate goal is to have autonomous robots helpful to people. Then one way you can approach that is to come up with helpful abilities. For example, object search is the focus of this work. You can like sort of try to focus on one ability at a time. And then we in this thesis we sort of just consider navigation-based action or language interaction. But you can imagine other different kinds of action or interaction. And one research agenda is that you sort of like focus on this ability, but connect it with like different things like manipulation, for example. One question I think about a lot is like how do you open drawers to find objects, or how do you use tools? So for example, sweep underneath the bed to like find something underneath the bed. So how do you make robots be able to make those kind of decisions? And another thing you could do is like, I'm also interested to move more into manipulation, sort of like focus on some fundamental problem there and then integrate what you find to be applied to different abilities. And also you can work on like a combination of two, like the dial object search, for example, like you're deciding what to say and how to act. And also you can imagine that language could help you like solve manipulation tasks more faster or something. So the hope is that it also could be applied to different abilities. And that's it. And I like to like thank my advisor Stephanie. It's a true pleasure to have worked with you, and I've learned so much. And I think I really appreciate all the help and the environment that you helped create. And thank my committee. I will not talk too long, but it will be in the acknowledgements. And thank my collaborators and staff, and Suzanne and Lauren and Kathy, who helped me order a GPU, and Eugenia, who managed organize the lunch outside, and John. And just some pictures over the years. It's interesting. Yeah, anyway, I'm going to skip and thank you.
We have a bunch of questions during the time, which is great. Are there other questions from the general audience?
Here.
Yeah, so super cool work. I was curious in some of, especially like in your first two projects, the robot will like often stop and take photos and things like that and like stop for a while. So I'm kind of curious, what's the main limitation from it kind of just continuously moving around?
Yeah, so the main limitation is really like the object detect doesn't work well when you have a blurry image. If you have the robot move around, I initially thought it would be like nice to have it like sort of like continuously do object detection, but it's actually giving you a lot more false negatives. So that's not good. Thanks.
I was just curious with the object detection work, and maybe this just isn't an issue at all, but how do you differentiate regions in your octree that you haven't gathered observations yet because maybe they're occluded versus regions that you haven't gathered observations yet because they're inside of a large object and you just can't see inside?
Cool. So the question is, how do you differentiate between like occluded objects or regions in the container?
Yeah, I guess like occluded regions or just like occupied regions.
Right. So in this system, the work that I've done, I didn't treat them differently. To me, like those are like sort of like just equivalent space in the 3D space. So you could have a prior that makes you believe more likely that the object is in the cabinet, but you don't have to treat them differently. Hey, Ben.
Mentioned treating objects as points. I had the thought, for example, when you were looking for the cat under the couch, that's plausible because the cat is small enough to fit under the couch, but maybe the dog is too large to fit under the couch. So is there work to be done there in terms of like common sense, physical reasoning about size? Does that
Yes.
fit into the model?
Okay, so the question is how do you handle like a larger object with objects of different sizes?
Or like
So
physical reasoning
Right.
more broad?
I see. So I guess the correlation work, was spatial correlation, but if there's some correlation between the size of the object and you can perceive the size, then you could like the same probability model could be used in the observation model as well. Yeah, I think that a lot of this is like, do you have the perception capability? Like if you see the table, and you have a bounding box around the table, could you like project the table to be like an area on your map instead of just a point? So often it's actually not so easy. Like so your bounding box could include like things that are outside of the table. That's messy.
Let me just follow up on that, because I think that there's a slightly different point maybe, which is if you know you're looking for a baseball bat, right? There's certain regions that it couldn't possibly be in, right? Given your current octree and your understanding of the occupancy, like there's no possible way that it's in my desk drawer. And so the question is, how would you approach
Right.
that?
So the question is like, how do you think about geometry constraints when you're searching
Basically,
for
that's
that?
right.
So yeah, so I'd say like, if you have a geometric representation of your search environment, like you have like, you can reason about like shapes and volumes, then you can see if like the shape you're searching for is like fits somewhere. But that could be, I'd say you could also have like I think of this like a lot of this is that you can think about the theory side or the implementation side. And for a system perspective, it may not be that hard to be basically, I have this current octree belief and this area, like I can possibly like segment my octree belief to get this area, which is like seems to be too small. And I just like knock that out in the system implementation. So.
Any questions on Zoom? Any real folks?
Hi, Kaiyu, this is Rohan. I have a quick question.
Go ahead.
You can hear me, right?
Yes.
Yeah, so throughout this talk, you discussed a lot about modeling problems as POMDPs, but you didn't really talk about the solving the POMDP side. In my experience, like POMDP solving is riddled with approximation issues. How did you kind of cope with solving large POMDPs and get good solutions?
Okay, so the question is, how do you solve POMDPs in this like real systems like this? So I'd say like practice. So in the initial 3D object search work, I didn't use any heuristics in the rollout policy, and I sort of relied on like having multiple planning like resolutions and try to select the best one. But later I realized that the POMDP planner, like the multicolored traces, really does is affected a lot by the rollout like heuristic in your rollout. So I did use heuristic of like basically during planning you can sample, you get a sample of the state and you see if like which action like brings you closer or can actually make you observe the object, and that's part of the sort of like the heuristic rollout. So another thing is I sort of like implemented the POMDP planner myself, so I sort of like could have a lot to like customize during, but not too much customization. It's mostly like just implementing the algorithm and changing the applying a heuristic in the rollout. So yeah, okay. Is there anything else? Please.
Great work. So my question is kind of naive. So for the robot to be able to actually set an object, you have to train it to be able to detect objects first using using images, right? So I'm thinking moving forward, do you think it's possible for this object to generalize to images it hasn't been trained on, maybe using text and maybe attributes and so on? I think it's possible for that moving forward.
Okay, so the question is, could you generalize the ability to search to objects that you haven't been trained on?
Just using text, maybe call something search for like clue.
Yes. So I think that's an interesting question, and I think people in the lab like Kyle is working on a question like that. Basically, the object that you're searching for has never been seen before. And you like to have a detector that can detect like an object that's described by a natural language phrase. And so for me, like if you have a detection capability like that, I can sort of integrate that into this planning process and it can still work. But the sort of perception side is a different question.
Can a lay person ask questions?
Yes.
Oh,
Yeah.
okay. Okay, thank you. I was wondering if the octrees, the structure of it, how does that relate to like an actual map, like a grid map, or do they are they similar? Or is
Sorry. So the question is, how do you impose the octree on top of the room that you're searching in, right? So right, so you can imagine like the room that you're in right now. You can like you can divide it into like cubes, and you can imagine basically some lines are drawn so that you have like a grid over the room that you're in, and octree is essentially just a grid, but some grids have like bigger resolution than others, and yeah, so that's, you can imagine like you can draw a picture of a room and then you draw more lines for sections. That's how you. So does that help?
Oh yes. Mm-hmm.
Thanks.
Any more questions, remote person? Awesome. Let's thank Kaiyu one more time. Everybody who's not faculty is outside, and there'll be a celebration or consolation outside.